AI development. And what is the AI environmental footprint? First, look at energy. How much energy does training a large AI model consume? Here you can see some statistics. For example, 2020, GPT-3, the energy it was consumed, it is equivalent to the average annual energy use of 120 USA homes. A single version of BERT was estimated to produce 1,400 pounds of carbon dioxide, the same as a round-trip transcontinental flight. GPT-4 in 2023, we talk about high energy use, possibly multiple gigawatt hours. And why so much energy? Because training on hundreds of billions of tokens, word symbols code, this is a scale of data. Training involves millions to billions of parameters updated over weeks or months on clusters of GPUs, graphic processing units, and tensors processing units, TPUs, and redundancy because training often includes multiple runs and experiments, increasing energy use. The repeated training also and tuning. The energy cost grows when models are fine-tuned repeatedly for different tasks and when developers run high-parameter searches, training the model many times with slight variations. So what are some mitigation trends? We try now to create, to improve our models. So we talk about model efficiency improvements, some more powerful models, some hardware advances are there. Renewable energy use is something which is recommended in data centers. And instead of retraining, some companies now are starting to release pre-trained models for reuse. So, of course, what affects energy consumption has to do with several factors, with model size, with data size, dataset size, training time, hardware use, the energy efficiency of the data center, the power source. So what are the difference in energy usage between training and inference? Training, actually, a large AI model can consume a massive amount of energy, often measured in megawatt hours or even gigawatt hours, depending on the model size and training setup. So this is a real-world comparison. Here you can see the numbers are equal to the energy consumptions of 120 USA homes. And the carbon footprint of GPT-3 training was estimated to 500 tons of carbon dioxide, depending on electricity sources. So how does AI energy usage compare to what was happening in the past, traditional computing systems? AI energy usage can differ significantly from traditional computing systems, depending, of course, on the type of task, the scale of deployment, and the hardware used. So first, we'll talk about the energy used per task. In traditional computing, we have low energy consumption. Here, the AI systems, much higher energy consumption. Training large models can consume megawatt hours, as I said before, of energy. And the inference means using the trained model, also uses more power than traditional apps. The training and versus inference models. When we train AI models, this is extremely energy intensive. For inference, there's less energy needed. And here we can mention also what we call edge AI, these on-device models, which can be optimized for efficiency, and this actually can help narrow the gap. The hardware efficiency, traditional systems mostly rely on CPUs. Now we use also AI accelerators or TPUs. These are more power hungry, but also more efficient for preparation for AI tasks. And what about the energy efficiency trends? We have new models, AI models like GPT or Google Gemini to be more compute efficient. Hardware also is evolving now towards low energy use. This is the trend through techniques like pruning. We're going to explore what is this, edge AI, quantization, and the cost of scale. As AI scales globally, the total energy demand would exceed that of many data centers if they are not carefully managed. So here you can see what is happening, what was happening in traditional computing, and now that is happening now. And what about the carbon emissions? Training cutting-edge AI models involves extensive computing over weeks or months, leading to substantial carbon emissions, especially when powered by fossil fuel-based electricity. So what is estimated carbon footprints here? For GPT-3, the carbon footprint in 2020 was 552 metric tons of carbon dioxide. And this is the energy, 1,200 megawatt per hour. And what is interesting to see is that this is equivalent to driving a gasoline car over 1 million miles. And the annual emissions is equivalent to the annual emissions of 100 average Mesa homes. Oh, sorry, stop sharing the presentation. We'll share again. Sorry, we'll start sharing again. Can you see now my presentation?
Yes, it is available.
Okay, thank you. So, for example, in 2022, we have the DAL-E model, which also estimated that this resulted in 300 to 600 metric tons of carbon dioxide, depending on electricity source. The GPT-3 in 2023, it is considered as more carbon intensive than GPT-3, of course, because we talk about a larger model size, more training steps. And the estimates by independent researchers suggest that the carbon dioxide emissions may exceed 1,000 metric tons, assuming fossil-based power. So here you can see the factor of electricity source. This shows the effect of carbon footprint. The data set and efficiency, it's more efficient, less waste energy. The model size architecture, bigger models means more compute, higher emissions. The training duration, this has to do with weeks or months of GPU clusters, reuse versus retraining, etc. So how can reduce the Airbus the AI's carbon footprint? This has to do with training. When we train when clean energy is available, so carbon-aware scheduling, at the Green Energy Power Data Center, which is already happening in Iceland, for example, the model optimization and the transparency tools companies like Hugging Face now provide carbon calculators for model training. And how do carbon offsets or renewable energy usage by AI companies impact overall emissions? No, carbon offsets and renewable energy use significantly influence influence the overall emissions associated with training and running AI models, but their effectiveness depends on how they're implemented. So when AI companies power the data centers with renewable energy, for example, wind or solar or hydro, what is happening? Direct emissions drop dramatically. For example, when we train a model with hydropower, this has lower, of course, emissions. Some companies like Google and Microsoft try to reach 100% free energy by matching users with real-time clean power. Here, what is happening in Iceland, Norway. In Norway, we have mostly hydroelectric. In France, we have what is a grid mix. We have mostly nuclear renewable energy. In USA, mixed fossil fuels renewable. In China, coal heavy. In India, predominantly coal. And the carbon offsets, as I mentioned before, carbon offsets are used when emissions cannot be avoided. What is happening? Companies offset their footprint by funding projects like for deforestation, renewable energy developing countries, carbon capture and storage. However, offsets are controversial because some of them are low quality, they are poorly monitored, or they're temporary, and critics actually argue that offsets often act as a license to pollute rather than drive real change. So what is the impact of this? That offsets can help, but only if they are high quality, permanent, and verifiable. They are a supplement, not a substitute for cutting emissions. So what is the bottom line here is that renewable energy has to do with real emissions reduction. The offset is a compensatory, and their effectiveness varies. And the best practice is what? Is to use renewables first, then offset what you can't eliminate. Now, regional electricity grids directly affect the carbon emissions of AI computing because the carbon intensity of power varies dramatically depending on the energy mix, coal, gas, renewables used in a given region. So carbon intensity is measured in grams of carbon dioxide, depending on the grid. For example, here, we can see the same model, same hardware, but here you can see with clean grid, we have low carbon dioxide. In Iceland, they use hydropower, so here you can see the difference. The inference location matters. This means that if it's this deployed globally, these services can rely on distributed data centers. Cloud providers like Google or Microsoft, now they are able to offer low carbon regions to minimize emissions. So what is happening here that we have a company request to clean energy data centers, and this can reduce their operational carbon footprint. So the carbonizing AI with grid awareness, here you can see ITER strategy, geographic scheduling. Then we can run jobs when local energy is available. The grid-aware load balancing, the carbon-aware training tools. There are tools like Cold Carbon to monitor emissions. We're going to see other tools also, and green cloud options, which are committed to 100 renewable energy. So you can see another table, summary table, and now about the model design. What is happening with the model design? What are the trade-offs between model accuracy and environmental cost? Actually, there is a clear trade-off between achieving higher accuracy in AI models and the environmental cost of doing so, because as models become larger and more accurate, their computational demands and therefore energy consumption and carbon emissions rise disproportionately. So some optimization strategies that could be the knowledge distillation. This means that smaller models that train to mimic large models, reducing cost while retaining accuracy. This is what we call knowledge distillation. The transfer learning and fine-tuning. This is another strategy to balance this trade-off. This means reuse pre-trained models, and this saves massive energy over retraining from scratch. The model compression, what we call pruning or quantization, this trims model size with minimal loss in accuracy, and architecture innovation, because efficient models now, like Distilbert or MobileNet, are using for this reason. So sustainable AI requires smarter compromises where good enough performance is favored over perfect accuracy, we could say, especially for real-world large-scale applications. So how can AI researchers optimize model architectures for energy efficiency? They can actively optimize model architectures while maintaining or improving performance through this technique, removing redundant or less important parameters, weights from the network. This results in smaller models that require fewer computation, less energy. For example, pruned versions of large models can maintain accuracy with 3 to 70% fewer parameters. Quantization, this means reduce the precision of weights and activations. So this lowers memory use and speeds up calculations and leads to lower energy usage or specialized hardware without big accuracy loss. The efficient architectures, so design models with fewer parameters but high expressiveness. Examples include efficient net, which balances depth with and resolution, the sparse transformers, which focus computations only when it's needed, mobile nets, and other lightweight models for edge devices. The knowledge distillation I mentioned before, when we train a small student model to mimic a large teacher model, student models are much smaller and cheaper to run, but retain much of the teacher's accuracy. Adaptive computation, this means that models that are dynamically adjusted computation per input, and this saves energy by avoiding unnecessary calculations. The neural architecture search for efficiency when we use automated search methods to find architectures optimized for energy and latency constraints. So what we can see here that researchers combine now these approaches to build AI models that are more energy efficient. They enable faster training and inference with a smaller carbon footprint. So model compression and pruning play a crucial role in reducing environmental impact. All these powerful techniques that reduce the size of a neural network without specifically affecting its accuracy, and removing less important or redundant parameters from the network to make it smaller and less computationally demanding are very important nowadays. And how they reduce environmental impact, because we talk about lower computation, less memory usage, faster inference, energy efficient training, and enable edge development. So some quantitative impact examples, the model size reduction, the energy savings. Smaller models can lower inference energy usage by up to 50 to 80% in some cases. And by reducing energy usage, compression directly cuts associated carbon dioxide emissions, especially critical at large inference scales. So the life cycle impact now. The training sometimes requires additional effort, but may speed up fine-tuning training later. The inference, we talk about major energy savings, especially at scale, and deployment. This enables the use in energy-constrained environments. So the benefits about its deployment: cuts cloud energy usage and emissions, reduce retraining needs, so lower energy use, a smaller model size, less energy for computation and memory. And what about hardware and infrastructure? Data centers play a major role in the environmental footprint of AI. Why? Because they provide the infrastructure that powers AI computations. So data centers consume huge amounts of electricity to run the servers that train and serve AI models. AI workloads, especially training, require powerful GPUs, TPUs running continuously, which increases energy demand significantly compared to traditional workloads. Second, it's about cooling requirements, because servers generate a lot of heat. So data centers use extensive cooling systems, air conditioning, for example, liquid cooling. And this cooling can account for up to 40 to 50% of total data center energy use, further increasing, of course, environmental impact. Carbon emissions, I mentioned before. This depends on the energy source powering the data center. Data centers running on fossil fuel-based electricity contribute more, of course, to greenhouse gas emissions. Those powered by renewable. And what about the resource use? This, you know, that building and maintaining data centers requires materials, rare earth metals used in chips, and materials like steel and concrete. And these materials have their own environmental costs from extraction, manufacturing, and transportation. And what about the scale growth? AI's increased popularity means more data centers are needed, or existing ones must be expanded. And this scale up can amplify the environmental footprint unless energy efficiency and green energy adoption keep pace. So it's important to say that data centers are the energy backbone of AI. They contribute to the carbon footprint primarily via electricity consumption and cooling needs. The overall impact depends heavily on the energy mix powering these centers and the efficiency of their operations, and industry tends towards greener data centers aim to reduce this footprint. What hardware innovations are helping to reduce the energy footprint of AI? The TPUs, as you before, the TPUs, the field programmable gate arrays, application-specific integrated circuits, because hardware plays a crucial role in the energy efficiency of AI training. So over the years, specialized innovations have emerged to deliver more compute per watt, helping cut the environmental impact of AI. So innovations driving energy efficiency. This is what we mentioned before, there's some models, and we talk about mixed precision equalization support, because newer hardware supports lower precision computations, which consumes less power but maintain accuracy. Hardware level sparsity, because chips now support sparse matrix operations, skipping zero values in computations to save energy. Advanced cooling and power management, because data centers use liquid cooling and AI-driven power optimization to reduce overall energy waste. And edge AI chips, because now devices like Apple's neural engine enable AI inference at the edge with very low power use. And here we can see what is happening with the difference between edge AI devices and cloud-based AI systems. What are the pros and cons? So for edge AI, it's the benefits is that we talk about reduced data transfer for efficient hardware. The negatives is limited compute power and device lifecycle impacts. On the other hand, the cloud-based systems, the benefits is that we talk about high compute efficiency, access to powerful models, but the negative point is data transfer energy. So what is which is a more sustainable? You will ask me, edge AI or cloud AI? For simple inference tasks with local data, like smartphones or Internet of Things, edge AI can be more energy efficient. For heavy training and complex inference, cloud systems are often more energy efficient overall due to optimized hardware and scale. So sustainability improves when cloud providers use renewable energy and efficient cooling. The best approach often involves a hybrid system, leveraging edge AI for low power, real-time tasks, and cloud AI for heavy processing, optimizing energy use and sustainability across the board. And what about the AI water that I mentioned before, since we talk about the water crisis? AI data centers consume significant amounts of water, primarily for cooling purposes, though the exact amount can vary based on location, on infrastructure, and usage patterns. So what are the general estimates that additional data centers can use approximately 1 to 5 million gallons of water per day, depending on their size and cooling technology. And AI data centers, which run high-performance compute clusters, like training models like ChatGPT, can use more water due to higher energy density and heat output. We can give some specific examples. Microsoft says that training GPT-3 consumed 700,000 liters of clean water. Google, again, we have huge numbers. Meta, the same. So what are the key factors affecting water use? The cooling method. Evaporative cooling uses the most water. Air cooling uses little to no water, but is less efficient. Liquid immersion cooling and direct-to-chip systems are emerging alternatives. Of course, the geography, climate is another factor. Data centers in hot areas often use more water, unless alternative cooling is used. The carbon for electricity, because hydroelectric and nuclear power, which are both water intensive, can of course raise the water footprint due to power generation. So how does AI related water use vary? Said before, this varies by region. The hotter regions often require more water and cooler. The water availability is stressed. In water-stressed regions, using large volumes of water for AI cooling is more problematic and often tightly regulated. Cloud providers may locate AI infrastructure in water-abundant regions to minimize environmental impact and public scrutiny. About infrastructure and energy also sources, we talk about this. Data centers near hydroelectric plants might use more water for power generation indirectly. Regions reliant on thermal power have a higher water use for electricity production needed to run AI workloads. And of course, it depends on the season. So what are some practical impacts we could say here that companies like Google, Microsoft, Amazon have already recognized that AI model training can consume millions of liters of water, depending, of course, on the factors that we said before, the season, location. And some companies already have started to shift AI workloads between data centers based on seasonal water efficiency, a strategy, what we call workload shifting or temporal load balancing. So what alternatives now exist to reduce water usage? Some key alternatives are air cooling. This uses ambient air or chilled air instead of water to cool equipment. So free cooling draws in cool outside air to maintain data center temperature. The water recycling, the reuse. The streets reuses water used in cooling systems. All of this, of course, have pros and cons. Liquid immersion cooling submerges servers in no-conductive cooling liquids that absorb heat more efficiently than air or water. The locational strategies, when we build data centers in areas with naturally cool climates or abundant non-potable water sources, in AI optimization workload management, this tries to reduce the need for cooling through smarter software and hardware design. So a combination of all these strategies often gets the best results. Another negative aspect of AI has to do with electronic waste and how the rapid demand for specialized AI hardware contribute to global AI waste. Because, of course, AI models evolve faster and the hardware needed to train and run them must keep up. AI accelerators are replaced within 2-3 years, much faster than general purpose CPUs. And older hardware becomes obsolete quickly, even if still functional, leading to premature disposal. And also, AI workloads require massive clusters of high-powered chips. This means more units are produced and eventually discarded, increasing e-waste volume. Cloud providers often retire servers when hardware is no longer economically efficient, even if it's still working. And the difficulty of recycling AI chips, because AI chips contain rare earth elements, gold, silver, and other critical materials. And these are hard to extract and recycle due to miniaturization, due to complex multi-layered structures, thermal paste that hinder separation. So more e-waste ends up in landfills or is processed unsafely in some countries. So AI-driven also obsolescence, this means that as AI adoption spreads across industries, companies are pushed to upgrade hardware regularly. And this accelerates turnover, not just in data centers, but in smartphones, in surveillance systems, in autonomous vehicles. Much of this old hardware isn't repurposed, it's discarded. And the environmental toll of manufacturing disposal, this means that manufacturing AI chips consumes large energy resources, water, toxic chemicals. So disposal releases heavy metals and toxic fumes, especially when it's incinerated or informally dismantled. So what we can say that the rise of AI accelerates a fast tech cycle where hardware is consumed and discarded faster than it can be recycled. This is the problem. Without circular economy policies, without better recycling technologies, without longer-lasting AI hardware, this trend will significantly be problematic. And we all know that the typical lifespan of AI compute hardware is 3 to 5 years, but this can vary, of course, based on several factors. AI hardware is replaced frequently because performance lapse, energy efficiency, the model complexity, software optimization, because this may support newer instructions now that accelerate training. And what are the practical considerations here? That some hyperscalers often rotate hardware every 2-3 years to stay competitive. Some AI startups and smaller companies may extend users to 5+ years due to cost constraints. And after primary use, hardware is often repurposed for less intensive workloads or resold on other markets. So, here we can see that rapid turnover leads to increased e-waste and embodied carbon. Companies are exploring hardware reuse, modular upgrades, and AI workload scheduling to extend life cycle. So what practices can AI developers at tech companies adopt? Definitely, we can adopt sustainable designs, responsible procurement, and end-of-life management practices. So design for longevity and reuse. This means modular hardware design. Create components that can be easily upgraded or replaced without discarding entire systems. Durability focus. Use materials that extend the hardware lifespan. Software updates. Refurbishment and reuse programs. This means internal repurposing. This means donation or sale or buyback programs. Responsible procurement. Use recycled materials. Life cycle impact assessment. Evaluate environmental costs before purchasing new hardware. The e-waste audits. This means that we need to track hardware life cycles to identify underutilized equipment, and the e-waste reporting also publicly disclose the recycling rates to promote transparency. Partner with certified recyclers, embrace AI for sustainability. So we talk about predictive maintenance and optimization tools, design models and software that are less resource intensive to run all older or more efficient hardware. Minimize impacting waste and advocate for right to repair and policy improvement. Support legislations that allows users to repair their devices without avoiding guarantees. So in summary, we could say that in order to reduce e-waste and improve hardware recycling, AI developers at tech companies should do what? Should design smarter, longer-lasting hardware, should extend life cycle to reuse and refurbishment, choose partners and suppliers with strong sustainability credentials, engage in ethical recycling practices, and advocate for structural change. So these steps can significantly reduce the environmental impact of AI infrastructure, while at the same time saving costs and enhancing public trust. So the best practices has to do with data efficiency, lifecycle management, transparency reporting, energy-aware training, efficient inference, hardware infrastructure, and the tools and platforms that track sustainability. Here we can mention some of these tools. Cold Carbon tracks energy usage and carbon dioxide emissions during model training. Green Algorithm, an online calculator for environmental impact. The model for model optimization, we have other tools, NVIDIA, TensorRT, etc. TensorFlow model optimization toolkit. For cloud infrastructure platforms with sustainability focus, for example, Microsoft Azure or Google Cloud, we have sustainability focus. So the checklist here that we can start tracking emissions with Cold Carbon or Impact Tracker. Then we can use a model pruning categorization with TensorFlow. Then we can choose cloud regions powered by renewable. We can monitor in time workloads with electricity map and publish carbon impact when we share models. This is example of a checklist. Of course, AI ethics frameworks play a crucial role because this helps ensure social equity and foster long-term thinking, guided transparency and compatibility. Of course, the AI is a part of the problem, as I mentioned before, but at the same time, it can help us definitely to monitor and reduce carbon emissions. On the other hand, we need to acknowledge the power of AI in help us tackle climate change, because we can, with AI, we can optimize electricity distribution, we can balance supply demand, we can integrate renewable sources to reduce reliance on fossil fuels. We talk about predictive maintenance also, renewable energy forecasting, about transportation. AI can help us with autonomous vehicles, electric vehicles, in manufacturing, with carbon tracking, in agriculture also, precision farming, in buildings also, with urban planning. And some solutions, AI solutions for emission reduction, Google DeepMind, Microsoft AI for Earth, IBM Green Horizon. So why this helps? Because AI processes fast, complex data sets that humans can easily analyze, because they're about real-time monitoring, and because it forecasts future emissions on energy demand, enable proactive management. So we can say that AI is actually both a potential part of the problem and a powerful tool for solving climate change. It helps us with it's about, on the other hand, it's an energy-intensive training. I mentioned before about what data centers, what is happening there. The AI workloads increase demand on data centers, which have big environmental footprints. The electronic waste that I mentioned before, the rapid hardware turnover for AI accelerators can increase the waste. But on the other hand, AI helps us fight climate change because it helps us with climate modeling, with smart agriculture, with carbon capture. So the key here is to balance the act, is to minimize AI's environmental footprint through efficient architectures, through clean energy, etc., while maximizing its climate-positive applications. Organizations and researchers are increasingly focused now on green AI, developing sustainable AI that balances innovation with environmental responsibility. And what would be the risks of unchecked AI development and global resource consumption? That if we don't check this development, then we will have exponential energy demand, increased carbon emissions, resource depletion, inequitable access to resources, and neglect of sustainability. The pressure sometimes to innovate quickly can deprioritize energy efficiency, what is happening now, and sustainability in AI research and development. And what will be the broader impacts in economy? Rising energy costs and resource scarcity could impact industries beyond tech. Environmental degradation affects vulnerable communities, fueling inequality and conflict. And regulatory, because governments may impose stricter regulations or taxes affecting AI development trajectories. So unchecked AI development risks cause massive energy consumption spikes, increased greenhouse gas emissions, resource extraction and pollution problems, growing e-waste challenges, and social economic inequalities. So we need stronger regulations about this. So governments should regulate the energy of AI training and development. They need to track the environmental impact, to promote energy efficiency, so can incentivize, for example, or require companies to adopt more energy efficient hardware, or to optimize algorithms for lower power use or switch to renewable energy sources, to leveling a playing field, because without regulation, some organizations might cut corners on sustainability to gain competitive advantage. Government insight ensures all players adhere to responsible practices. And public accountability, because since AI development impacts society broadly, governments have responsibility to protect public interest, including environmental sustainability. So, these regulations, already we have what is the current landscape of environmental policies related to AI. We have some general climate energy regulations. Many countries have broad regulations targeting carbon emissions. Examples include carbon taxes or renewable energy mandates, energy efficiency standards for data centers. Some other regions have specific policies on data center or data center energy efficiency. For example, the European Union Code of Conduct for Data Centers, which encourages best practices for reducing energy consumption. There are other organizations promote ethical AI principles that include environmental sustainability. We have European Union AI Act proposals, UN Sustainable Development Goals, and policymakers are actively exploring mandating carbon footprint reporting for AI models, incentives for using renewable energy in AI compute, and guidelines for energy efficient AI strategy. For example, the European Union digital strategy includes sustainability as a key goal. So this is the current landscape. Of course, the key challenges could include that rapid innovation, AI innovation outpaces regulation, Measuring AI's environmental impact is complex, and balancing AI benefits against its footprint. These are the challenges. So finally, before concluding, I will mention about the transparency, how it is important for tech companies to be transparent. Already, companies like Google, again, I stopped sharing. Okay, some companies like Google or Microsoft publish reports or blog posts on AI energy use. Many companies are vague or silent. So what we need is transparency, why it matters, because transparency helps users, investors, policymakers to make informed decisions. And this, of course, encourages companies to improve efficiency and adopt clean energy, and this drives innovation in green AI practices. So thank you very much for your attention and patience. Green AI is the need of the hour, and I think to raise awareness about what is happening every time we write a word on ChatGPT, how we harm the environment. Thank you.